Hi guys, today we're going to review systems of equations. So in this chart right here, we have the three different types of systems of equations. In our first example, we have two lines, and where they cross would be our one solution. So when we have two lines like this, they're going to cross exactly once, right? Only once, and we'll have one solution. That solution is a point x comma y. These two lines are consistent and independent. They're independent of each other, and it's consistent because they have one solution. In our second example, it shows two lines, except the two lines are right on top of each other. In this case, because they're right on top of each other, we have an infinite many solutions, or an infinite number of solutions. Basically, both lines will have every single point in common. Remember that we don't say all round numbers because it's only the points on these lines that are our answers, not points off the line like this one right here. So all of these points actually on our line are part of our solution, and there's an infinite amount of solutions, but not all solutions are our answer. And because we have an infinite amount of solutions, our systems of equations is consistent, and the two lines do depend on each other, so it's consistent and dependent. In the third example, we have parallel lines. When we have parallel lines, there are no solutions because these two lines will never cross. And they are inconsistent. The two lines, it's inconsistent because there is no solution. In our next example, we'll be graphing these two systems of equations in order to solve them. So in our first equation, y equals 2x minus 2. Remember that this is in slope-intercept form. Y equals mx plus b. We'll be starting at our b, which is negative 2. And then we'll use our slope. Our slope is 2 over 1, so we'll go up 2 over 1 each time to find all the points on our graph. If we wanted to find points on the left-hand side, we'd go back to negative 2 on our y-axis, and we'd go down 2 over 1. You notice all of these points make a line, so we'll carefully draw out a line here. Use a ruler on your own paper. And then we'll start on the second equation. Our second equation is y equals 1/3 x plus 3. So we'll start on our y-intercept of a positive 3. And then we'll use our slope. Our slope is a positive 1/3. Positive meaning we'll go up 1. Positive 3 means we'll go to the positive 3. And we can now see where they meet. They meet right here. Right? We could draw our line. Remember that if you want to find points on the left, go back to the positive 3 on your y-intercept, and you can't go down 1 over 3 to continue this line. And draw out our line, and we can see where they meet. You do always have to write your answer as a point. A point is x comma y. Okay, so our point right here, we're meeting at the x value of 3. You just kind of go down. And we're meeting at the y value of 4, so our point is 3 comma 4. In our next example, we'll be solving the systems of equations by graphing, but now we're given both of our equations in standard form. So in order to graph these two equations, we do have to solve them so that they're put into slope-intercept form. So we'll take our first equation, x minus 2y equals a negative 4, and we'll start putting this into slope-intercept form. We'll subtract our x. So we have a negative 2y equals a negative x and a negative 4. And now we can divide everything by that negative 2. Our slope-intercept equation is y equals a negative divided by a negative is a positive, and we'll have a positive 1/2 x. Here, a negative divided by a negative is a positive, so we'll have plus 2 as our y-intercept. And now we can graph this. We'll start at plus 2, and we'll go up 1, over 2. Up 1 over 2. If we want to find points on the left-hand side, we'll go back to the y-intercept of 2, and we'll go down 1 over 2 to the left. Down 1 over 2 to the left. Draw out our line. And now we get to start all over with the second equation. So 3x minus y equals 3. We could use the same process as subtracting the 3x and then dividing by this negative 1. Or, because it's just minus y, let's move the y to the right side of the equation by adding it. And let's move the 3 to the left side of the equation by subtracting it. And we'll be left with 3x minus 3 equals y. Right, and if we rewrote this y equals 3x minus 3, that would also be in slope-intercept form. So we can do that. Now to graph it, we'll start at negative 3, and we'll use our slope of a positive 3 over 1. Okay, so we'll go up 3 and to the right 1. Up 3 again and to the right 1, and now we can see exactly where they meet. And we always have to write our answer as a point. This answer is 2. Oops. Comma 3. In this example, we'll be using the process of substitution in order to solve our systems of equations. In substitution, we'll be taking one of our equations has to either be x equals or y equals. In this equation, we have x equals a negative 3 minus 5y. So we'll be plugging this value, negative 3 minus 5y, in for x on our other equation. So we'll start by rewriting our equation 3x minus 2y equals 8. And in our parentheses, we'll plug in the value negative 3 minus 5y, and we'll solve. So now we can solve this equation. 3 times negative 3 is a negative 9. 3 times negative 5 is negative 15y. We have our minus 2y, and that equals 8. We can combine like terms, so a negative 15y and a negative 2y is a negative 17y. We can now add the 9 to both sides, and we'll get negative 17y equals 17. And if we divide by negative 17 on both sides, we'll have y equals a negative 1. Now that we know what y is, we'll have to solve for x. So if we take our equation, x equals a negative 3 minus 5y. Here's our third way of solving a systems of equations. In this example, we're going to use elimination. In elimination, we're going to eliminate one of our variables, either x or y, by adding or subtracting our equations. In this example, because we have a 1x and a 1x, we're going to use elimination to eliminate the x's. In order to do this, we need one of these to have a positive x, and we need the other equation to be a negative x. So for our second equation, we're going to take the entire thing and multiply it by a negative 1. And now we'll rewrite our two equations. We have our first equation, x plus 2y equals 6. Our second equation, when we multiply that negative, we'll have a negative x, a positive 3y, and a positive 4. By doing this, we'll have a positive x on our first equation and a negative x on our second equation. X minus x crosses off or eliminates. And now we can add the rest of our equations together.
a positive 2x and a positive 3x gives us a positive 2y and a positive 3y gives us a positive 5y. A positive 6 and a positive 4 gives us a positive 10. Divide by 5, we'll get y equals 2. Now we'd have to solve for x. So what we can do is we can plug our y of 2 into one of our original equations. I'm going to use this first one right here. X plus 2y equals 6, but we're making our y 2. So x plus 4 equals 6. And if we subtract our 4, we get x equals 2. So our answer is 2, 2. Here's our second example of elimination. In problem 2, we'll be eliminating by using multiplication. In order to eliminate a variable, they have to have the same coefficient but opposite signs. So we have a 3x and a minus 12x. We could make them both 12, a positive 12 and a negative 12. Or if we wanted to eliminate the y's, we could make this y a negative 4y and then we'd have a positive 4y. That's what I'd like to do. So we're going to multiply our top equation by 4. If we do that, we would have 12x minus 4y equals 4. In the bottom of the equation, we would have a negative 12x, a positive 4y, and that equals 3. 12x and negative 12x crosses off. That's 0. Negative 4y and a positive 4y crosses off. So on the left side of our equation, we have nothing. On the right side of our equation, we have positive 4 and positive 3, which is 7. Remember that when all of our variables cross off and we have a fault statement, our answer is no solution.